In this video, I would like to do one example regarding the ideal gas. So in this example, we have steam at a given pressure and temperature, and the question is asking whether steam is behaving as an ideal gas. Now, if you remember, we had exactly the same type of questions in thermodynamics 1. Pretty much the same thing, nothing new. The reason that I decided to do this was just to do one review, but don't think that there is something new in this discussion. No, absolutely what we did back in Thermo 1. So, if I want to decide whether a gas is behaving ideally or not, what I want to do, I want to find the z value in this correlation. So the correlation is PV equal to ZRT, okay, ZRT, okay, and this V is supposed to be in lowercase, like this is the pressure, this is specific volume, and if in order to answer this question, what I want to do, I want to obtain the z value, and depending on the value of z, I can answer this question. Is if z is close to 1, then yes, the gas is behaving ideally. If z is far away from 1, then it is not behaving as an ideal gas. Okay, so basically, in another word, the question is asking to obtain the value of z. Okay, okay, so let's do that. This z depends on the reduced pressure and the reduced temperature. So PR, which is the reduced pressure, is equal to pressure over the critical pressure. All right, so we have two states, by the way. So first I'm doing for the first state, which has this pressure and this temperature. So pressure of 88 megapascal and temperature of 970 Kelvin. So the pressure is 88 megapascal. This is P subscript CR. Okay, so this is the critical pressure. You want to use table A1 to obtain this critical pressure. So if you go to table A1, you will see that for this substance, which is basically water, so it says steam. If you go to table A1, you do not directly see the word steam, but in fact, steam is the vapor phase of water. So what you want to find in this table A1, you want to go all the way to the to the end, probably just one before the last. This is water, and these columns are basically giving us the critical properties. So you want to use this column for T critical and this column for a P critical. So for water, the critical pressure is 22.06 and the unit is megapascal. Okay. 22.06 megapascal. So, and that ratio is roughly equal to 4. Okay. Now you do the same calculation to obtain TR, the reduced temperature, which is the temperature over the critical temperature. So the temperature is given at 970 Kelvin. The critical temperature comes from the same table. So you go to same table and you read 647.1 Kelvin for water. And that gives you a reduced temperature of around 1.5. Okay, now these are the two numbers that I have, and then based on these I go to figure A15 and obtain the value of z in that figure. So I use these two and I go to A15. So let's do that. In figure A15, what we have is the PR on the horizontal axis and TR as bunch of curves. So let's say my PR, my reduced pressure is 4. Okay, so this shows the reduced pressure PR. The horizontal axis is PR. And then this is PR equal to 4. So my point is somewhere on this vertical line, simply because my PR is equal to 4. And in the calculation, our reduced temperature was 1.5. Now, these green curves are the reduced temperature curves. I'm not sure if you can read, but it says TR equal to 5, 2.5, 2, 1.8, 1.6. What you want to find TR equal to 1.5, which is exactly this one. Okay, so getting back to our point, our PR is 4 and our TR is 1.5, which is exactly this point that I'm pointing at. And then after that, you horizontally go to the left and you read the Z value. So let's say RZ is around 0.8 for this particular state. Okay, so from A15, we get Z value equal to 0.8. Now, because Z is not close to 1, then the gas or the steam is not behaving as an ideal gas at this pressure and at this temperature. So the answer for the first state is the gas, or let's say steam, is not behaving as an ideal gas at pressure of 88 megapascal and temperature of 970 Kelvin. Now, the question that sometimes the student asks, and that's frankly a very good question, is how close should we be to 1 to say that the gas is behaving ideally? That's a really good question. So you know what? To answer this question, I would refer you to this figure A15. This line I'm pointing at Z equal to 1. So this is Z equal to 1. Just look at the curve or the figure and consider an envelope or a margin, let's say from here to here, a very small margin before and after 1. As long as we are in that margin, then we can assume that the gas is behaving ideally. For instance, this is 0.9 and this is 1. I would say maybe anything above this line, which is Z equal to 0.95, and also anything less than here probably is the condition that the gas is behaving ideal, at least in our course, at least in our contract or convention. So if your Z is just roughly between 0.95 and let's say less than 1.03 or 5, doesn't really matter. At least in our course, we call it an ideal gas. Okay, maybe depending on the problem you're solving, you may want to consider this is equal to 0.95 into this equation, but in our particular course, we don't really bother to include that in this equation. So this was for the first state, and the problem statement gives me state B with another pressure and another temperature. So let's do state B as well. So for state B, we have the pressure of 99 megapascal and this temperature, and I'm doing state B in another color. So pressure is 99 megapascal and temperature is 1455 Kelvin. All right, the procedure is still the same. My reduced pressure is pressure over the critical pressure, PCR subscript CR, which is 99 megapascal over 22.06 megapascal, which is equal to roughly 4.5. So that's my reduced pressure, which by the way is a dimensionless number. And my reduced temperature is the temperature over the critical temperature, which is 1455 Kelvin over the critical temperature of steam or water from table A1 is 647.1 Kelvin, and that gives me a reduced temperature of 2.25. All right. Once again, you use these two numbers, you go to figure A15, and based on that, you will read Z value equal to 1.05. Okay. So On the exam, I don't put you in tough situation to make a decision between yes and no to answer this question. If the guess is behaving ideally, I make sure that z is really close to 1, maybe it's even far away from 1. And so don't really worry about like deciding whether the answer is yes or no. If you even show me this calculation, if you show me that you know how to do that, then you are good. But yeah, if we want to stick into this convention, well, we say no, the gas is not behaving ideally. But the answer of yes and no is not that important, because in engineering life, we want to do calculation. So what we do, we just put this z into that correlation. All right. Again, on the problems, I don't put you in tough situation to make a decision for a z that you don't really know if that is close enough to 1 or not. But anyway, so this was the procedure to answer problems like these. We did that back in term 1. Very important kind of calculation. So yeah, definitely use figure A15. Know where you want to get PR and TR properties. Both of them are coming from A1. And that's pretty much it.